Alright, hello and thank you for coming to watch my YouTube video on floating point numbers. So I'm making this YouTube channel to help some people, hopefully with either numerical analysis or finite element type problems. Specifically, I want to make Python code for finite element problems and some numerical analysis with examples of how to generate those codes to help people, because I feel like there wasn't enough examples when I was doing some of them, and I just kind of want to put a few more out there. But got to start at the basics. So I figured I'd start off with floating point numbers, kind of talk about how these systems work, why we use them, and what the IEEE standards are that the hardware you're watching this video on right now uses, and some of the pitfalls where you can magnify error, overflow, underflow, how we store special numbers, and then I do have a little example at the end for one of the consequences of using these number systems. But without any further ado, let's get into it. So you can see I wrote out this little equation at the top. If you haven't used floating point numbers before, this equation up here is definitely going to be new to you. So what I'm saying is that the floating number representation, called a word, for x is going to be equal to this first plus or minus, which is my first bit. We start talking about how many bit, whether 32, 64, 128. This fraction right here, or the mantissa. So this is going to be your precision number. Actually, I put an n here, but that's going to be the t down here in a little bit. And then I have beta in the denominator all the way. So that's your base. In binary, that number is 2. And then these D1, D2, D3, all the way to Dn up here is going to be your binary digit, or for your floating point representation. And then over here, we're going to scale this, and this is something that can cause headache for us later, by your base to some power e. And this e is integer. So the first thing I'd like to talk about when you use these numbers is that you can have, or you will always potentially have, some sort of error just representing a number in the first place before you even do any operations. And so that error can come in two forms when you represent your x. So we'll say for some x minus float of x. So the actual value before I represented it, and now that's represented, is going to always be less than or equal to some value. And this value, when I go from x here to float of x, so when I map it in, I'm going to multiply it by g times beta to the e, so this stuff. And we're just going to say I got the sign right and everything, and we're going to kind of ignore the g part because it's not super important. This value is always going to be less than 1/2 times your base to the 1 minus precision times this b of e. So the scaling factor is really, that's what I'm going to call it, can really cause some issues for you if you can't see yet. So then what we do is we say, okay, well, how about our relative error? So we'll take this magnitude and divide it by the magnitude of x. And we basically just are going to get to cancel out that b of e there. Or not b of e, beta to the e. Right? So then we get this. And this particular number right here is of significance because that's called your rounding unit. So here we'll say this rounding unit, eta, is defined as 1/2 times your base, the 1 minus precision, and that's important and has a nice little feature in binary. So let's say we're floating point representation in 64-bit. So in 64-bit, 11 are going to be for a fraction of what's representing whatever beta is to the power of, 11 of them. We're going to have 1 for this sign that I talked about earlier, so 1 there, and that leaves 52, and the other 52 are this fraction. So there's 52 in there. And then specifically for this case, we'll see that our rounding unit is 1/2 times 2 to the 1 minus 52, which is equal to 2 to the minus precision. So it's pretty cool, good to know. It'll definitely come in handy later. So the next thing I want to talk about is when we add, subtract, multiply, and divide, we can find ourselves magnifying errors. And the three things that you need to kind of pay attention to that can become an issue for you is 1, these are all going to be for some x and y. And these things are going to be, they differ widely in magnitude is what we're going to say. Yeah, widely in magnitude. So what that means is x plus y is going to have a large absolute error. Error. Sorry about that. And then the next thing is that if we make y really small, or we make y really big. Well, I don't even know, much bigger than 1. All right, so when y is really small and really big, we can have pitfalls when we use x over y, or x times y. And these are basically saying the same thing. That's going to have potentially large relative and absolute errors. So now that's a problem. And then if x and y are basically the same number, then, x minus y could get rounded down to 0 or near 0. And when that happens, you get a large relative error because it's basically 0. So it's definitely not a large absolute error when you think about it like that. Then we have a little bit of the basics down with our system. There are some special numbers that we want to model in the system. And this is going to be specifically in the IEEE standard. So it was laid out in the mid-80s, I think 1985. And then it was changed noticeably in 2008, but it's pretty consistent and it works really well. Our examples that I'm doing, I'm going to stick to 64-bit for you. So we're going to talk about 0 and how we're going to store that. So we're going to store all of this fraction. It's going to be zeros. And then the sign is 0, which means positive. And then the beta to the e. All right, so then this value right here, e, is going to be stored as e minus l, or excuse me, it's going to be called minus u, the upper limit, from whatever number is here in this 11-digit expression. So in this case, we are going to make it all zeros for our expression. So these are zeros. So it's going to be beta to the minus u, which now means that we are storing in here the smallest positive number that we can create. So smallest positive value equals 0. And then we'll talk about infinity. This can be a 0 or 1 in front. So that means it can be positive or negative. That looks like a division sign. We're gonna fix that real quick. It's gonna be positive or negative, and then this fraction right here, this guy, all zeros, and then this is gonna be all ones, and then for this case, we're going to end up doing, this doesn't matter right here, so you can have plus or minus, you can have 0 or 1. And then for our parentheses, what we're going to end up storing in here is something that is not equal to all zeros. And then, so it could be 1, 1, and all zeros, and that's going to be not a number. And then the exponential up there is still your largest value that you can make. Alright, so I was saying there's going to be something interesting we're going to see. If I tell you this is the smallest number you can make, you would normally think, if you weren't used to using these systems, that the next smallest number is probably going to be right around here. However, your next smallest number is actually it's gonna depend, but I mean, it's gonna be a lot closer. So you're gonna have a gap that's really small right here, and then a gap that's relatively large right here compared to it. I mean, both are gonna be small, depending on your system, but they're not equally spaced, and that's the whole difference between the relative error and absolute error. So for the absolute error, we do the x minus float, and this is x minus the float of itself over magnitude of itself. And then, so for that relative error, the relative error is going to be bound less than 1/2 times beta to the 1 minus t. And then for the absolute error, we're just going to multiply by whatever this beta e is. So it's relative error times that. Okay. Why does that happen? Well, let's consider an example. So we'll just start with, say we have some floating number system, and the e in this system, u equals 2, l equals -2. So the smallest number I can make then, and we're going to say I'm going to go out to, in binary, to 2. Oh, this is a 1 over 4. That was a 1, I promise. So if we want to make the smallest value I can here, we're just going to take these guys, make them zeros, and we're going to say that the smallest number I can make in this system then is going to be equal to 1. But yeah, the smallest number I can make in this system then is only going to be 1/4. As odd as that seems every time you do it. And then you'd be like, okay, well, how about this? What's the next smallest number? We'll call this one x0. So the floating point of x1 then, times 2 to the -2, which equals 5 over 16. And then we'll look at x1 minus x0. Look at the absolute value of this guy right here. And it's going to be 5/16 minus 1/4, which gives you 1/16, which, like we said, is equal to 1/4. And if we take this a little further, we could probably also go out here and gander that our 1/16, when we round, is going to be sent to 0. All right, so thanks for watching, and I hope you learned something.